In a convolutional neural network, an input tensor enters a layer and undergoes a physical transformation, emerging with different spatial dimensions and a new depth. Tracking these changes is difficult because the terms kernel and filter are often used interchangeably. To calculate a model's parameters and predict its output shape, we have to establish a strict distinction between the two. Think of a filter strictly as a structural container within the network layer. Here is an empty filter next to our flat incoming data grid. A kernel is the actual grid of trainable weights. Notice how this 3x3 kernel slides directly into the empty filter. Treating the filter as the housing and the kernels as the operational parts inside allows us to trace exactly how data is processed at every stage of the model. We'll start with the base case, processing a single-channel image using exactly one filter. Here is a one-channel input grid. With a depth of 1, the filter needs just one 3x3 kernel. As it slides, it computes the dot product, merging 9 pixels and weights into a single scalar value. That scalar is added to a single bias term. This combined number passes through an activation function, outputting a single pixel onto the new activation map. The math includes 9 weights plus 1 bias, giving 10 trainable parameters. Even in this basic pass, tracking the bias term is essential to understanding the full inventory of trainable weights within the layer. Now, let's look at a standard RGB color image. Instead of one channel, we are now dealing with 3 depth channels. This introduces a core rule. Filter depth must match input depth. Moving to a 3-layer input tensor, our filter expands to hold 3 separate 3x3 kernels. All 3 slide over their channels, computing 3 distinct scalar values. These 3 values are summed and added to the shared bias term. Since we used one filter container, the final result is a single-layer activation map. The parameter count updates to 27 weights plus the bias, totaling 28 parameters. Input depth increases the number of kernels and the total parameter count, but it does not change the depth of the output. To increase output depth, we need to detect multiple features simultaneously, which requires multiple filters. Using our single-channel input again, we apply 4 distinct filter containers. Since the input depth is 1, each holds one 3x3 kernel. Each sweeps across the input independently, generating its own unique activation map. These 4 individual maps stack together to form an output tensor with a depth of 4. For this setup, we have 4 filters, each with 9 weights plus 1 bias, resulting in 40 trainable parameters. The depth of the data leaving a convolutional layer is determined by the number of filters you choose to deploy. So now we can combine these rules into the general case, a multi-channel input processed by multiple filters. Here, a 3-layer input tensor is paired with 4 separate filter containers. Each filter contains exactly 3 kernels. The input depth dictates kernels per filter, while the filter count dictates the depth of the output tensor. To find total parameters, we multiply the filters by the sum of their internal weights and the single bias. 27 weights plus the bias is 28, times 4 filters equals 112 trainable parameters. With this formula, you can map the flow of data through any convolutional layer and predict exactly how the tensor dimensions will change. We can verify these calculations by looking at how deep learning frameworks report this data. This model summary breaks down the network's architecture. Looking at the Conv2D layer, the argument is set to 4 filters. That count corresponds directly to the output shape's final integer, confirming data depth. Finally, the parameters column shows 112, matching our calculations. Mastering the relationship between input depth, kernel limits, and filter counts allows you to trace the exact shape of your data through every layer of a complex architecture.